How to solve a differential equation using power series? First, we need to identify the points. You have ordinary points if they are not the zeros of the denominator for px and qx, or basically px and qx are both analytic. If they end up on the denominator, we call them singular points. The singular points are either regular or irregular. For a regular singular point, you multiply px by x minus x sub 0 and qx by x minus x sub 0 to the second power. If both of these get to be analytic, then you have a regular singular point. Take a look at this differential equation. You have 2x, the second derivative of y, plus 1 plus xy prime plus y equal to 0. So to identify singular points, we're going to divide by 2x. When you divide by 2x, x equal to 0 is singular because it's on the denominator. Very good. So you get 1 plus x divided by 2x as px and 1 over 2x as qx. Multiply px by x and then simplify, you get 1 plus x divided by 2, which is analytic, which is basically a polynomial. Multiply x squared by qx becomes x divided by 2, which is again a polynomial. So what's the meaning of that? It means that this singular point is a regular singular point. So applying the Frobenius theorem to solve the differential equation, you're going to use the following format, the summation Cn x minus x sub 0 to n plus r. Very good. Take the derivative, first derivative, and second derivative, and substitute that in the original differential equation. The first term is 2x, the second derivative of y. And the second derivative of y is this form. Substitute this guy here. Plus 1 plus x times y prime. The y prime is here. So you're going to distribute this into the power series. And finally, plus y. Y is the summation Cn x to power n plus r. Now, take a look at the first power series. The first power series is 2 times summation n plus r minus 1, Cn x to power n plus r minus 1. So starting at 0, the power is n plus r minus 1. The second power series is the summation n plus r Cn x to power n plus r minus 1. Again, starting at 0. The third power series, remember, we distribute this into parentheses. So that's how you end up with 4 power series. This guy is the summation n starts at 0 to infinity of n plus r Cn x to power n plus r. Guys, take a look at these powers. This is n plus r minus 1. This is n plus r minus 1. And now you end up with n plus r. And the last power series is starting at 0, going to infinity Cn x to power n plus r. Perfect. You can factor out x to power r and then start combining these power series together. Take a look. If I combine the first 2 power series, it is n plus r, and then you have n plus r minus 1 plus n plus r. So if you combine these together, you get n plus r times 2n plus 2r minus 1. Basic algebra, everybody. And then you have Cn x to power n plus r minus 1. Plus, now combine these 2 power series. You get n plus r plus 1 Cn x to power n plus r. Now take a look. You can factor out x to power r from both of these 2 power series and write it in front. Then you can just write down the very first term. Why is that? Because the exponent here is n plus r minus 1, and this exponent here is n plus r. And when you factor out x to power r, it becomes x to power n minus 1, and this guy becomes x to power n. So if you write down the very first term, you get r, this is 0, becomes r, times 2 times 0 plus 2r minus 1. So you get 2r minus 1, c sub 0, x to power negative 1 plus the rest of the terms. But now, if you write the rest of the terms, it starts at 1, all right? This guy starts at 0. You're going to make a little bit of adjustment. You're going to introduce a dummy index like k, and then try to combine these using the exact same index k. So k is defined as n minus 1, and k is just n. The way that we are representing this is to find a recursion between these two. So x to power r, write down the very first term here. You're going to use this to identify what are the r values and then combine these together to find a recursion. Very good. So when you set this guy equal to 0, r times 2r minus 1 becomes 0. R is 0 or r is equal to a half. Now, we're going to use the rest of the terms to find the recursion. You get k plus r plus 1 times 2k plus 2r plus 1 ck plus 1 plus k plus r plus 1 ck equal to 0. Again, this is just coming from the coefficient in general term here. Now, since you have two values for r, you're going to substitute them and see what is the formula. When r is equal to a half, this guy becomes ck plus 1 equals to negative ck divided by 2 times k plus 1. And when r is equal to 0, this guy becomes k plus 1, 2k plus 1, ck plus 1 plus k plus 1, ck equal to 0, or basically ck plus 1 becomes negative ck divided by 2k plus 1. Very good. Now plug in values to find C1, C2, C3, C4, and eventually sometimes you can find a nice relation between Cn and C sub 0 or Cn, C sub 1. Some other times you can find even terms pattern, odd terms pattern, but here in this general case, when r is equal to a half, using ck plus 1 equals to negative ck divided by 2k plus 1, these are the terms, and the general term can be written this way. So when r is equal to a half, the first solution is x to power a half, or square root of x, times 1 plus the summation of negative 1 to power n divided by 2 to the n factorial x to the n. However, when r is equal to 0, this is the recursion that we have. ck plus 1 is negative ck divided by 2k plus 1. So basically you have c1 negative c sub 0 over 1. C2 is negative C1 divided by 3, and so on. And this is the pattern that we see. This is the second power series solution. So we found two power series solutions for the differential equation, which is written here.